Hello everyone, a warm welcome, it's Toady here. Well, I've got a great video for you today. For a while I've been meaning to cover lunar laser ranging, which is bouncing strong lasers off the moon. It's a great topic as it proves we landed on the moon and also that we went into space. I was prompted to create this video because QE on Nathan Oakley's show the other day called me out, and as usual he's misled everyone. So here's the schedule. First, we'll take a brief look at what they said on the show. Then we'll get straight into the main presentation. We'll look at real scientific evidence and some real science. In pulling this video together, I actually reached out to a scientist who works at an observatory, and he shared some fantastic and exciting behind-the-scenes data and pictures with me. You won't find these on the internet or wiki, and it goes to show just what actual real scientists work on day in and day out. So, without any further delay, let's get to it.
Toady liar. He said that we know why it's hitting the moon because of mirrors left on the moon. So we fire a laser and we get a coded signal. Really, Toady? Did you know that in 1962, folks at MIT shot a laser to the moon and got a bounce? Where were the reflectors then?
Yeah, they were still being manufactured because the Apollo missions hadn't taken place yet. And
Okay, let's take a little look at these characters here. QE, also known as John Stunger, is, as usual, disingenuous and deliberately excluding key information to try and make his point. He seems to regard himself as some sort of modern-day Renaissance man, taking no hostages within the academic establishment. He is rude, confused, scientifically illiterate, and also extremely aggressive. He's also a regular on Nathan's show, which enables him a platform in which to spout his rubbish. Now, Nathan's not university educated. We all know that he was a grocery boy and a salesperson, and so completely unqualified to pronounce meaningful scientific ideas, either by training, education, or his experience. They both struggle with higher order ideas and like to remain within their safe space, guarded by their mute buttons, and they can silence all intelligent queries. Now, I don't want to go into a long bad mouthing of these two, as that's not the point of this video, and I'll probably leave that for another day. However, a couple of points are in order. QE has toe tagged me twice. However, that's all part of the rough and tumble of YouTube, and I feel rather special that I've been singled out for this treatment, even though I've never actually debated him. He was educated, as I understand it, as a dietitian, and I don't doubt that he's suitably qualified to recommend people to eat more roughage, consume less sugar, and so forth. But when it comes to thinking about high-order ideas, such as evolution, quantum physics, gravity, biology, chemistry, or mathematics, you can just forget it. His embarrassing bungling on many occasions has given rise to great humour for our group, and we now call this doing a QE. Recently, a notable example was his debunking of Google Earth, where John claimed that it proved the Earth was flat. He simply had no comprehension of how map projections operate or the difference between elevation and altitude. He's also well known for his pre-prep work, where he uses many rainbow colours, what he calls crown munching, and inserts little animated GIFs as a sort of chorus line, where he invariably sees them crying, laughing and gurning. They add a sort of bizarre contrast to the proceedings. Being academically trained at a first-class university myself, I've never seen the need to enhance my own presentations with such ephemera. The biggest issue I have with John and his work is that, as you saw, he will always attack, bully and close down any active debate. There's no room with Nathan or John for any kind of intellectual debate, high concept, meeting of minds, stimulation, humour, or even agreeing to disagree. We see from this instance that he's really keen to try and score a point over myself, and he completely manages to debunk himself and Nathan by affirming the fact that there is a physical moon and you can bounce light off it. The normal articulation from QE and Nathan are that the moon is either a hologram, a luminary, or just a light in the sky. So, let's move on and see some real evidence. Right, what are we going to show in this video? So we're going to have a look at the history of laser ranging interferometry. We're going to see how it works. We're going to see what we know about the lunar reflectors. We're going to look at some of the observatories which are independent of NASA that do these experiments. We're going to look specifically at how one of the observatories operates and works. Now, in this, it's very exciting. I've reached out to James Battat, who is a physicist who works at the Apollo Observatory, and he sent me some slides and some pictures, and we're actually going to see into the depths of how these things work, a lot more than you'd see just by Googling on the internet, and that's fascinating. Then we're going to look at evidence of the landing on the moon due to the results from the LRI. Then we'll look at the challenges that the observatories have and some indirect globe evidence from that. We'll have a little look at the evidence for gravity from this, and then we'll pick up with some final thoughts. Okay, straight into it. If we look at QE and Nathans Assertions, well, QE was very hasty at the end of the show on Nathan's Hangout that I played the clip from earlier to try to outsmart me with his assertion that lasers have been bounced off the moon before the Apollo missions. Now, what he says is absolutely correct. Indeed, lasers were bounced off the moon in 1962 by the MIT lab. Nothing wrong with that. But what does that actually tell us? It tells us two things. One is that mankind has reflected a signal off the moon, clearly. And then the second is that the moon is actually a physical object. Now, both of these things go counter to Nathan and QE's main narrative, that they don't know what the moon doesn't exist, the moon is a luminary, and it's certainly not a physical object up there in something called space. So I think that's absolutely fascinating that they've sort of debunked themselves. Now, what I'm going to show in this deck is that we can further conclude the following things. That space does exist, and that the moon averages 384,402 kilometres from the Earth in an elliptical orbit. Man has sent missions using rockets into space to place the 5 known reflectors onto the moon. That gravity exists, and the LRR ranging observations provide some general relativity evidence. And then finally that the Earth is a globe due to the adjustments which are required to baseline the LLR observatories. Okay, let's dip into the history of lunar laser ranging. Well, the first successful tests were carried out in 1962 when the team that QE spoke about from Massachusetts Institute of Technology succeeded in observing laser pulses which were reflected from the moon's surface using a laser that had a millisecond pulse length. Similar measurements were obtained later that same year by the Soviet team at the Crimean Astrophysical Observatory, and they used a Q-switched ruby laser. Though laser pulses were picked up by both the US and the Russian observatories prior to the moon landings, these signals were sparse and very erratic. It wasn't until the laser ranging retroreflectors were placed onto the moon that better and greater accuracy was achieved, and we'll see some of those actual results a little bit later. The USA placed a retroreflector array on July the 21st, 1969, and that was the crew of Apollo 11, and then 2 more retroreflector arrays were left by Apollo 14 and Apollo 15 missions. Now, the Russian missions, the lunar missions, which had Lunokhod 1 and 2 rovers, included retroreflectors as well to support laser ranging. Unfortunately, the Russians actually lost Lunokhod 2 for many, many years, and in fact it was only when the Lunar Reconnaissance Orbiter, the LRO, which this is a CGI picture of course, was put in place, that it managed, after spinning and orbiting around the moon, to find where Lunokhod 2 actually was, and the position of its reflectors in 2010. And this is what we're talking about. This is what a reflector array looks like. It's very similar, in certainly idea, to maybe the reflector on a bike pedal, or the back of your bike. What happens is it reflects light back at the incidence angle that it comes at. So if you put a beam of light and it goes in straight into this reflector, it will send that beam of light back directly. So it's very, very good for looking for, obviously, reflections of photons, which is why they use it on the moon. Okay, what facts have we got? Well, during 3 of the US Apollo missions, 11, 14, 15, and then the 2 unmanned Soviet missions, Lunar 17 and 21, retroreflectors were deployed near the landing sites between the dates of 1969 and 1973, and I'll show you exactly where those sites are on the moon in a sec. Now, the LLR experiment has continuously provided range data between the Earth and the moon for about 50 years. It's generated about 17,000 normal points. See the graph down here, and I'll talk through that in a sec. Now, the main benefit of this space geodetic technique is the determination of a host of parameters which describe lunar ephemeris, lunar physics, the moon's interior, various reference frames, Earth orientation parameters, and the Earth-Moon dynamics. And it's also used, as I'll touch on later, around general relativity. We can see here that most of the reflections really, or the point data, comes from Apollo 15, then next Apollo 14, 11, and then a little bit from the Lalakut. And we'll get into what this graph is a little bit later. By the way, all the way through this, I put the references below so anyone can pick them up, type them in, and look up where I got all this information from. Okay, here's a lovely picture of the moon in quite glorious high resolution. These are the locations of the reflectors on the moon, exactly where they are. There are 3 LLR reflectors on the moon placed there by the Apollo missions. As you can see, Apollo 11, Apollo 14, and then Apollo 15. And then 2 reflectors that were placed by the lunar missions, though of course they lost one for 20, 30 years. That's Lunar 21 and Lunar 17, which is showing exactly where they are. Okay, so how do you go about this laser ranging stuff? Well, you take a strong laser and you point it at the moon. You do that from normally an observatory with a strong laser in it. You send the signal out, that's 20 Hz pulses it uses. There's about a 2.5 second round trip, judging on the speed of light from the moon. And then you have about 50 pulses in the air simultaneously, and these are very, very powerful pulses. What do you do with it? Well, you aim at the retroreflectors, because obviously you need to bounce something back. Here you can see, I think that's probably Buzz Aldrin, placing one of the retroreflectors, and here you can see indeed one of the retroreflectors in place. We have to thank Buzz Aldrin, because it's 50 years and counting of bouncing things off the moon. And then of course the signals come back and they're picked up by the dish here. In this example it's a 3.5 meter dish, and we'll see a lot more about that dish a bit later because it comes from my contact James. Right, what do we know about lunar reflectors? Well, there's 3 of them on the moon and 2 Russian ones. We've already covered that. At the moon's surface, amazingly really, the beam is about 6.5 kilometers wide. That laser, which starts out very, very small, goes out to an absolutely massive size. Now, the scientists liken the task of aiming the beam to like using a rifle to hit a moving dime 3 kilometers away. So you can see it's incredibly hard, really, to hit one of the reflectors. The reflected light is too weak to see with the human eye, of course, because it's bounced back and come through the atmosphere. Out of the enormous number, 10 to the 17 photons that are actually aimed in the very, very powerful laser going out at the reflector, only 1 is received back on Earth. This is even under good conditions. Of course, you imagine those photons going out, you imagine them coming back, a lot will miss, a lot won't hit the reflector. If you imagine 6.5 kilometers wide and it's only a meter square, the reflector, first of all, lots of that 10 to 17 will just not hit anything. Then the ones that are lucky enough to get on the reflector will come back. They could hit birds and trees and bits of atmosphere and dust and goodness knows what that's in the way. So obviously you get very, very few back for all the ones that you send out. Now, they can be identified, these signals, because you might ask, well, how do we know they're picking up that signal? Why, they could be picking up all sorts of things. These photons could come from somewhere else. They can be identified as originating from the laser because this laser is coded, it's highly monochromatic. And in this case, it's obviously green light. Now, this is one of the most precise distance measurements ever made, and doing this piece of work is the equivalent in accuracy to determine the distance between Los Angeles and New York to within about 1/4 of a millimetre. And finally here we can see evidence of these 2 pictures that were taken on the moon. Here is from the Apollo 11 laser ranging experiment, and here is the Apollo 14 retroreflector. And this picture was taken by Alan Shepard, I think. Again, plenty of proof these things exist and are really there, up on the moon. Okay, the beauty of laser ranging detection is it's independent of NASA. Now here we have an example of 4 observatories. There are more, we're going to see another one in a sec. There's a number of them around the world that do these experiments. They're not funded or paid for by NASA, they're independent of NASA. This one is the McDonald Laser Ranging Station in Texas. This is the laser ranging facility at Wetzel in Bavaria, in Germany. Here is the BARDA 5.3 meter SLR dome for geodetic research in Finland. And finally, this is the Goddard Geophysical and Astronomical Observatory. And of course, all of them undertake these tests. They all have a big observation telescope, which can pick up the light, plus they aim it at the right place, and then they fire the laser out, and we'll see some examples of that in a sec. Now this one is called the Apollo, and it's at APO in New Mexico, and this is where James works. He sent me this information. Obviously it's quite high up, it's 2,788 meters. They want to get up out of all the gloom and the smog and lots of light pollution that's down below, so they like to put these observatories up high. It's got a 3.5 meter dish. Here's a lat long if you want to look at it, and then we're going to see more of this this detector very shortly. Here is the 3.5 meter gantry. The mirror is mounted in here, and the laser is mounted here, and we'll see the laser in operation in a sec. So it's quite a substantial setup in this observatory. Here we see the Apollo in New Mexico actually firing the laser. You can see the beam going out, and you can see a lot of the reflected light from powering up that laser. It's very, very bright, it's very powerful, it's got 10 to the 17 photons in it, and so indeed it should be. Here we can see the Apollo laser ring. Of course, this is the highly monochromatic light. It's very, very green, as we can see. And this one is firing up. You can see the lasers pumping through it and then being pumped out. A very exciting picture. Okay, let's look at the detector. Well, these detectors are made by Lincoln Labs, MIT. They detect single photons, which is really quite amazing. They're about 50% efficient, and they have a 50 picosecond timing jitter. Now, what's this timing jitter about? Well, effectively, when you're getting lots of pulses in a short time back and they're hitting your detector, you want to make sure, because the detector, once it's detected a photon, has to reset itself, and that takes a little bit of time before it can detect another photon. And if you're trying to detect many, many photons in a short, very short, nanosecond period of time, you need to get a lot of recovery. And so this is why they're talking about the timing jitter. These are very good detectors, these APDs. Here we can see the laser actually firing. Again, you can see the green light, and you can see the excitement within this setup they've got in the box for pumping that powerful laser in. It's really good to get a first-hand view of this. It's very hard to find this stuff on the internet, so I'm very thankful for James for sending me this. And here we can see what's going on at the back. We've got the timing electronics up at the top. We've got the laser that we've just seen in the box. We've got the APD detectors that MIT make down here, very, very close to where the signal's coming in. We've got the control computer over here, and then there's some kind of thermal controls, because they want to cool down to make sure the detection works correctly. So thermal controls, very important. What are we looking at here? We said we'd dig into this more. So this graph shows December the 8th, 2005, data from the laser that's being repeatedly shot at the Apollo landing site. Where you see a dot, that is where a photon is reflected back from the moon. Now the dark line that we see here, this shows where a large number have returned at a very specific time. It indicates that there is something very reflective there, but small, well under a meter in size. Now photons reflected back from the surface come back over a much broader range of time, ones that randomly bounce off the surface of the moon, don't bounce off the reflector. As we see, the whole vertical range of this plot corresponds to only about 30 meters in range. So from here to here corresponds to about 30 meters. This little black line corresponds to about 1 meter. And there are less of them, and they have no grouping. The concentration of photons at a specific time appears when the laser is aimed at either Apollo 11, 14 or 15 landing sites. Otherwise, the expected featureless distribution is observed. This is a really good independent evidence of NASA placing reflectors on the moon, just as they've claimed. Now let me dig into this graph a bit more. Along the bottom we've got time in minutes, and we can see that between 0 minutes and about 12 minutes they took a number of observations. Now going up the vertical axis, that shows us what they call the time into the gate in nanoseconds, so very, very small periods of time. These are semi-random photons that have bounced off somewhere the surface of the moon, and these have bounced somewhere off the surface of the moon. But we're getting no clustering effect. We're seeing random bounces where some of them have bounced and they've managed to come back and they have been picked up. But it's sort of a lot like noise. But what we do see is that the 45, maybe 50 nanosecond period, we see a huge cluster of photons coming back, all very, very heavily grouped during the whole of this 12-minute period. So this tells us that there is a small object there that's highly reflective and is sending a vast number of those 10 to the 17 photons that go out back, and it's being picked up by our detectors. Now, there could be no reasonable argument to dismiss the fact that when a laser pulse is shot at the location where we expect to see a lunar ranging reflector, and then we see a clear signal response that's in line with our expectations, This confirms we have a mirror, as expected, at those locations, and it is reflecting light back to Earth. There is no other reasonable explanation for why this black line happens, and we get these measurements. And we get them across at least 5 different independent observatories, independent of NASA, across the globe. Over a number of years, by the way, as we see there's about 50 years of this work been going on. Okay, evidence of the landings from the data and the results. This is where it all comes together. The detection on Earth of reflections from moon-based laser-ranging retroreflectors, LLRs, these reflectors that we've already seen, is evidence of landings. These LLRs were positioned as lunar ranging experiments for long-term studies, and indeed, as I've alluded to, we saw those results from 2015. There's been results going on for a long period of time. If we quote from James Hansen's biography of Neil Armstrong, First Man, The Life of Neil Armstrong, for those few misguided souls who still cling to the belief that the moon landings never happened, examination of the results of 5 decades of LRR experiments should evidence how delusional their rejection of the moon landing really is. Now, the NASA independent Observatoire de la Côte d'Azur, the McDonnell, the Apache Point, and the Hilakala observatories regularly use the Apollo LRR. Lick Observatory attempted to detect from Apollo 11's retroreflector, while Armstrong and Aldrin were still on the moon. But they didn't actually succeed until August the 1st, 1969. Now, why would they want to do that? Why would they be trying to bounce stuff off this while they were still on the moon? The reason's really obvious. If you can detect it while they're still on the moon, you know the reflector's in the right place. If you can't detect it while on the moon, it's very difficult to send somebody up there to adjust the retroreflector. So if you've got dust on it, if you put it in the wrong angle, if it's looking the wrong way, if you can't find where it is, these are really big problems for trying to actually bounce something off it, clearly. Now, the Apollo 14 astronauts deployed a retroreflector on February the 5th, 1971, and the McDonnell Observatory, that's the one that we saw earlier, detected it the same day. They have a very powerful laser there. The Apollo 15 retroreflector was deployed on July the 31st, 1971, and that was detected by McDonnell Observatory within a few days. So they have a really big successful hit rate, and obviously they found these two, while people were still on the moon and just coming back. Okay, finally, just to show that there's other results other than the ones I've shown, there's a whole paper here of all the experiments they've done, including the Russian ones. I would advise you to look up this PDF. It's really very interesting. It's got some pictures in it. Pictures aren't great, but the graphs and the information is very good. Here I'm showing some of the 1971 results. Again, we can see them over this 5 nanosecond period. And finally, on to more evidence for the globe. So I'll read this out quite quickly, but it's fascinating stuff. Any laser ranging station, the Apollo one included, measures the transit time and hence the distance between the telescope to the reflectors. But for lunar ranging science, what's really wanted is the distance between the centre of mass of the Earth and the centre of mass of the Moon. To do this, the position of the telescope and the reflectors must be known to be comparable within a few millimetres. Since both the telescope and the reflectors are stationary structures, it might seem that this could be precisely measured and their position would be known. This assumption is not too bad for the Moon, which is quite what we call a quiet environment, but the Earth, there is a lot of problems. So we'll go through them. The Earth's polar axis moves and the Earth's rotation is irregular. The polar axis moves due to various causes, some predictable, for example the Moon exerts a torque on the Earth's tidal bulge, and some are variable, rocks are rebounding from the last ice age or the weather. Weather also affects the Earth's rotation by moving large masses of water around. These effects, important to many other science projects as well, even have their own agency to keep track of them, called the International Earth Rotation and Reference System Service. So it's amazing, they've actually built up a special body to keep track of these movements because they affect scientific discovery and observation so much. Next up is the stations move due to the tides. The Moon, since it's tidally locked to the Earth, has relatively small and repeatable tides of about 10 centimetres. The solid Earth has larger tides, oscillating about 35 centimetres peak to peak every 12 hours. So of course that needs to be taken into account, because as we can see, where the laser is fired from is moving, potentially, over 12 hours by 35 centimetres. And that will change the timing. When you're looking at nanosecond timing of the signal coming back, a movement of 35 centimetres obviously blows your experiment out. Next up, the Earth's crust changes in response to long-term fluctuations, such as post-glacial rebound. In other words, because the glaciers have moved off the Earth is rising up. The Earth's short-term weather can also affect the location of the telescope. I found this one fascinating, primarily vertically. Various weather effects can actually load local regions of the Earth's crust, depressing it by a few millimeters. These effects come from the atmosphere, high-pressure systems pressing the Earth's surface, and the ocean, water piles up on the coastal, depressing the crust. Groundwater fluctuations caused by rain can also affect the telescope's location. So basically, if it rains near one of these observatories, or it rains on it, again, it can depress and it can change where it is. And finally, the pressure of sunlight. Now, this is mind-blowing. The pressure of sunlight itself pushes the moon slightly off-center. This is a small effect. It's about 3.6 or 4 millimeters, but it's particularly important since it mimics the effect of EP violation, which is to do with general relativity, which is what they're looking for. EP is the equivalence principle. So it's an important part of relativity. And they're trying to use these LLRIs to do a lot of experiments around general relativity. Now, 4 millimeters when the sunlight is on the moon. So when the moon is all lit up, it's literally being pushed by that light, pushed by those photons, pushed by those millions and millions of photons 4 millimeters away from the Earth. And then final, continental drift needs to be compensated for. So all of these things show that there are global effects which move the position of the observatory. We can see these, they're cyclical, we can model them, we need to take them into account and then remove them when we're doing our experiments. So here's a final summary. Lasers fired at the moon reflect photons and we can measure them on Earth. We can study the distance to the moon, and through the variations we can look into general relativity and the violations of the strong equivalence principle. Various factors can create changes in location, which is what I just spoke about. The largest ones being the lunar crustal tides, 4 meter changes, Earth crustal tides, 20 centimeter changes, and then finally the pressure of the photons coming from the sun, solar radiation pressure of about 4 millimeters. The error factors help confirm that there is a globe by their very nature. We've just seen that. Precision measurements of the distance between the observatory and the LLR on the moon shows relativity elements, which is why they've been doing it for 50 years. The measurements are undertaken independent of NASA and provide evidence that support the moon landings by both Russia and the US. And so this means that space exists, rocket and astronauts obviously exist, and the moon is real. And it's also a physical object. It's not CGI or illuminary. Because we placed laser ranging reflectors on it, we can measure them and see the results. Final point about gravity, Einstein, and the Lunar Laser Reflectors. Again, I've given both the sources. So the first one is about general relativity. Almost all of the most accurate tests of general relativity are currently derived from the LLR, from the Apollo arrays. Over the long term, we expect to improve the current accuracy of these tests by a factor as large as 100. These include many of the PPN parameters as well as G dot and G ant, the violation of the LR2 law, whatever that means. This will address many tests concerning the validity of general relativity at a new level of accuracy. This is especially important as we confront two of the major issues in fundamental physics, astrophysics and cosmology. These are the conflict between the current formulation of general relativity and quantum mechanics, and that interrelation. And then number two, the role and reason for the acceleration of the distant galaxies, i.e. dark energy. So they're using these bounces from the LLRs from the moon to look at some of these absolutely fundamental ideas. And the second piece is this. LLR has also become one of the strongest tools for testing Einstein's theory of general relativity in the solar system. No violations of general relativity have been found so far. However, the basis of all scientific analysis is more high-quality data from a well-distributed global LLR network. And I think the key there is global. There's a number of these observatories across the globe. So I want to wind up. I want to say a big thank you to everyone for listening. Hopefully this has been of interest. We've gone through at quite a pace about the moon landings, the mirrors, the reflectors, how they're placed there, the evidence. We looked at the graph, we looked at the data, and then we looked at some of the problems associated with them. And hopefully this has finally answered and debunked a lot of the nonsense that we've heard from Quantum Eraser on Nathan Oakley's show. You know, lots of personal attacks and ad homs against me and myself. I don't want to get into that. You know, QE has difficult problems about how he explains things about science, you know, and his idea on observations and what a scientific experiment is. At some point we'll debate those, but I think I want to leave that for now because I think the point has well been proven. And indeed, we have been bouncing photons from lasers off the moon and measuring the distance for quite some time. Thank you very much.